So, Daniel, can we get started? Daniel? Yeah, welcome to all the attendees of this InSIS webinar that we have been organizing for the last 2 years. So today our speaker is Mr. Daniel from the Czech Republic, and he is going to talk today about the design, development, and validation of mechanical properties using a portable instrumented indentation system. He is representing a company which is UTMdev, right? And it's in Ostrava in Czech Republic. And to give you a brief of the speaker, Daniel Omacht. Daniel, as what I call him, is a seasoned engineer specializing in research, innovation, and development of unconventional testing machines, equipment, technologies, and devices. He graduated from the Brno University of Technology in 1995 with a degree in engineering and subsequently obtained certification as an international as well as a European welding engineer. His entire professional career has been dedicated to research and development. He has held various positions, including mechanical engineer, programmer, research scientist, and ultimately the head of the research, development, and production department for testing machines and equipment. In 2020, he founded UTMdev Limited, a company specializing in research and development and production of unconventional testing machines, equipment, and devices for testing miniaturized samples using methods such as small punch test, which is called as SPT, instrumented indentation testing, IIT, and the non-destructive material sampling, creep testing of miniaturized samples using small punch creep test and the impression creep test. He's contributed to numerous significant national and international projects, including RMTVC, RMTVC-PU, and the TK01020160, focusing on comprehensive approaches to materials engineering to ensure the safe operation of innovative blocks in both conventional and nuclear power plants. He has also achieved several notable results, patents, utility models, and collaborated on the European testing standard EN 10371 for small punch test metallic materials. So today he will talk about his journey through the kind of development of the miniature testing systems which are used for obtaining the mechanical properties of materials. So with this few words of introduction, now I pass on the stage to Daniel. And as what you can see in this list, there are a number of other colleagues with whom we are all interacting as part of the small specimen test techniques community. And we will now listen to Daniel for his lecture. Thank you.
Thank you very much for introduction, ladies and gentlemen, dear colleagues. Let me tell you some words about our research in the area of design, development, and validation of mechanical properties using portable instrumentation test system. The content of this presentation is visible in this table. My presentation is divided in five parts. In the first part, I will tell you some small mention. I will have a small talk about IIT principle. In the second part, I will tell you about our engagement in IIT development. In the next part, about IIT evaluation methods. Next part will be about verification of IIT evaluation method. And the last part will be about industrial using or using of our equipment in industry. As I said, the first part of this presentation is about instrumented indentation test principle. As it is visible in this picture, you can see the indentor. Indentor is in the shape of the ball, and we use indentor in the shape in the diameter from, we can say, 0.2 millimeters up to 5 millimeters. The principle of the testing is gradual pressing of the indentor into the material, while the force and depth is measured. For our testing or for evaluation, we use 15 cycles of the instrument indentation test. In this video, you can see how it works. The principle is very simple. Indentor goes inside the material and back. But in our testing is not precisely in this way, because we don't go out of the material fully. We go only 40% of the maximum force in what is in each cycle. What do we get by this method? We will get the curve, testing curve, as it visible in this chart. And in the curve, you can see 15 steps, 15 cycles. So it means 15 steps. What is the purpose of IIT, of instrument indentation test? It is, or we use it for determination of mechanical properties, as a yield stress, tensile, ultimate tensile strength, Young's modulus, Brinell hardness, strain hardening component, strain hardening constant, and accumulated yield strain, or for determination of fracture toughness. Here we can determine K1C, or determination of residual stress. IIT is in China and in India is covered by standard, and in Europe we have an ISO technical report 209-381. The biggest advantage of IIT it is that after the testing we have only we can see only very small imprint in the material, because maximum imprint of by our IIT test method is 150 microns depth. And practically or generally we can say that, just a moment please, I'm sorry, that the advantages of IIT, generally we can say that it is a fully non-destructiveness. Device can be used in industrial, but in lab conditions too. The machine is easily portable because it has only 6 kilos in our case, and the manipulation can be very fast and precise. But the main advantage is it is instant evaluation, so you can get the results almost immediately. Testing can be done in any position. It means that you can test in vertical position, in horizontal, or in upside down position. Of course, every method has got some limitations, and IIT is in this way is the same. Limitations of this method, it is surface cleanness, for example, because you need a spot or the place for testing what is sufficiently clean. For this, for this we need to grind the surface, and final surface or for preparation final surface is enough 320 grits. The next limitation, it is the hardness of the material. Our indentor is made of tungsten carbide. It means we can indent, we can test the materials that are softer. In our case, we tested, or the main aim of the testing are for the main groups. It is a low carbon steels, low alloy steels, austenitic steels, or high strength steels at this moment. And now, or recently, we are working at the other models, mathematical models, what are convenient for copper, for example, and aluminium and plastic materials. So in the future, we will have the next 3 mathematical models. Next limitation of instrumentation test, it is a surface flatness. Flatness, in this way, I am speaking more than about the surface flatness, about the perpendicular of the indentor to the testing surface. It's necessary to have a perpendicular position, and a limitation can be the time, because each test can take from 7 up to 15 minutes. Plus, we have to calculate that in each place, we have to do about 7 tests. So together, we are speaking about 1 or 2 hours we need 1 or 2 hours for 1 test. Only shortly about history of our IoT development. We know that at the beginning, or the beginning of instrumentation method, or maybe automated indentation method, it's about in 1972, maybe a little earlier, but of course it was developed because computer were developed, so it was hand in hand together. Our interest, I'm speaking about the interest of our research group, started in 2012, and we started to develop our first prototype of indentation machine based on the draft standard N675. We can say after four prototypes, we built about 4 prototypes. And we can say the first one was not successful, the second one was better, the fourth one was good, but it has about 16, maybe 18 kilos. So it was a good machine, but not completely perfect for industrial conditions. In 2020, we were contacted by Dr. Jingzili and his team. He told us that he would like to have a cooperation with our group, with our research team. And he said that he spent more than 7 years on the evaluation of IIT. Based on this, we started cooperation, and the cooperation was very tight. During the COVID time, almost 2-3 years, we spent together. Almost every year we were in contact. We spoke about the details of the machine, of the testing results, and so on. We modified our small punch grip testing machine, what you can see in the picture on the left. And to be possible to do IIT test at this system. And after, as I said, 2 or 3 years, when we were satisfied with the results, we started to develop our final version, or the final version of IIT machine, what will be possible for using in industrial conditions everywhere. This type of the machine was called as a PIIS 3000. 3000 is maximum force what is possible to use it. for testing. It is 3 kilonewtons. What is very important, it is evaluation or the way how to evaluate instrumentation test or the testing curves. I mentioned that in these days are 3 or 2 standards and 1 technical report. All the details are, or the basic frame of the evaluation is described in these documents. In this presentation, I will tell you only shortly what we did. These standards shows that there are 3 methods. The first one is representative stress and strain method. The second one is inverse analysis by finite elements. And the third one is a neural networks. We use all 3 methods, but for the calculation, we use representative stress and strain evaluation method. This method is based on the definition true stress and true strain points. Everybody of you know how does it look like, or how looks like typical engineering stress strain curve. When we measure the cross section during the test, we will get true stress true strain curve. And just from our 15 cycle curve, we needed to get 15 true stress true strain points, and subsequently correct interpolation give us the correct results. I mean yield strength, ultimate tensile strength, Young's modulus, Brinell hardness, strain hardening exponent, and others. This in this presentation only shortly. What is the accuracy of our evaluation? Because the basic frame we used from the standard. Of course, we made a lot of modifications. The accuracy of our modifications you can see in these 2 charts. For yield strength and ultimate tensile strength, it's up to 10%. The accuracy for 4 groups of materials is, in my opinion, is very high. How is it with the fracture toughness evaluation method? I mentioned that Dr. Jingzili and his team focused not only in mechanical evaluation, but fracture toughness evaluation method too. The basic concept of indentation energy to fracture energy was created by Bayern in 1998. The principle is calculation based on the damage Young's modulus, what is calculated from unloading slope. You can see only a small output from our evaluation. More details, it's beyond the scope of this presentation. But what is very important, it is the part number 4, because as I said, we wanted to develop the machine what is possible to use it in industrial conditions, mainly in power industry or nuclear power industry. And from this reason, we have 4 models for the most used materials in these industries. And verification was necessary. The most common material in power industry, you know, it is P91. And in this picture, you can see 3 tables. 3 tables. In the first table, you can see 6 tests, as it visible here in this chart. 6 tests and evaluation of this test in average value. And In the second table, you can see the average value, what was obtained by standard tensile test, 3 tensile tests, average value, and comparison. And you can see that for yield strength, it's about 1.9%. For ultimate tensile strength, it is deviation 4%, and for hardness test is 2%. Here you can see some details from the evaluation software. The same what you can see what you saw at P91. We did at many materials, P92, P22, plus materials what are used in nuclear research, nuclear power energy, and so on. P92, for example, here you can see 4 tests, and the proof of the accuracy of the machine what we created, it's visible in these curves. The standard deviation is 0.2%. So the curves are almost the same. Again, if you can see the comparison, you can see the result, 2% difference between yield strength, ultimate tensile strength is 4%, and Brinell hardness is 1%. How is it with the high strength steels? At this is high strength steel. You can see one part or 2 parts of the sample, part A and part B, and we measured fracture toughness, and you can see the average value is 87, and from CT test was 77. So difference is about 12% at part A, and at part B it is about 7.8%. If we realize how big is the specimen for CT test, and we compare with a very small imprint, in my opinion, it is very good results. Accuracy at the fracture toughness at this moment we have about up to 20%. In this table, you can see the summary of the materials what we tested. Not everything is in this table because it wasn't. The table should be much bigger. But you can see 3%, 5%, 2% differences. Based on these results, we decided to use this machine in industrial conditions. And in the last chapter of this presentation, I would like to show you the example of using this machine or IIT technology in industrial conditions. The first example is about material determination of mechanical and fracture toughness material properties of steam pipeline, as it is visible in this picture. We determined properties in 3 points. The first point, the second one, and the third. The first one was in the part what was replaced. You can see the welds. It was replaced with the new material, new pipeline. We are speaking about the pipeline with diameter 324 millimeters and with the thickness 40 millimeters. And plus we tested the elbow, but the elbow was old, was after the 250,000 hours of operation at the temperature about 540 degrees. And the third point was at the straight section of the elbow of the old pipeline, as it is visible here. As a first step, was necessary to prepare the surface. For this, we used standard grinder and as at the second step. We did in 4 steps, but it is not necessary to tell you all the details. But the second step, we can say, we used the polishing the wheel. After the polishing, we obtained 3 points. You can see it here. And these 3 points were tested. How did we do it? We did it by the help of the special, call it as a special, but it is not nothing special at it. It is a table. The table was fixed to the tube by chains, very precisely. Why do we use this table? Because the table, when you install the testing head, you can change the testing or place of the indentation because in 2 axes, in x-axis and y-axis, you can see digital measurement of the movement. So it means after the installation, you could see the full setup here. And after the installation, we started the test. The test is fully automatic. Only user will press the button start, and the test is, when the test is finished, you can see the sound signal, and you can move the indenter, for example, 3 millimeters aside, and you can continue with the testing. At the first position, we did 10 points, as it visible in this picture. At the second position, we made 7 points, and the same we did in the third position. Here you can see the testing curves from the place number 1, from the place number 2, and from the last point. Results or curves were evaluated by our model because we knew what kind of material it is. So we used low alloy model for evaluation, and results are visible here. Summary of the results are in this table. I will repeat. The first point was a new part. The second was in the middle of the elbow. I will call it as a critical part, critical place. And next to the critical place, it was a straight section of the elbow. It is place number 3. Graphical comparison is visible in this chart. So new pipeline is blue color. On the opposite, it is in the red color is a place, you can call it as a critical place in the middle of the elbow. And next to it, it is a green curve. Conclusion from this measurement was that in spite of the quite high temperature, because the surrounding temperature was about 50, maybe 55 degrees, everywhere was dust, quite vibrations. We obtain by IT totally 10 plus 7 plus 7. So totally we obtained 24 testing curves. And all curves were valid. You could see that the curves were not damaged, what was possible. All the curves were possible to use for evaluation. And expected pipeline parameters were confirmed because we expected that the parameters, mechanical material properties at the new pipeline will be the highest, and the critical point of the old pipeline will be the lowest. Yeah. And how is it with the fracture toughness? So we expected that during the aging degradation, the the highest K1C will be at the new part, and the lowest value will be in the critical point. And it was proved, and you can see that we tested the material. What was or the material of the pipeline was 14 MO 106.3, and you can see the table with the minimum values of this material, and we measured the values from 3 points, and in circle are the lowest values in the critical point. And with these values were compared with the minimum values what are valid for this material. So you can see that our values are significantly higher than minimum values. So from this point of view, we could say that the pipeline, in spite of fact of 250,000 hours of operation, can be operated further. Of course, must be judged from other point of views. The second example of using IIT in industrial conditions you can see in this picture, and it was measured at the power plant, coal power plant. Technologists determined critical places and they prepared the places for IIT measurement, and we measured, or our team measured the places, and of course we did the results in the report. Next example of using IIT, but not only IIT, it was used in water section of steam drum. Operator would like to know mechanical and fracture toughness material properties of the steam drum, inside part of the steam drum, and therefore we used our scooper. We scooped sampling material from inside part of this drum. Subsequently, we did small punch test plus evaluation of the microstructure and so on. And plus we made the IIT, and the clamping was done by magnetic system, as it visible in this picture. And the last example of using IIT in industry, it is evaluation of the material properties of the turbine rotor, and for this we used magnetic system. I have a very nice presentation about all the work, because we didn't use not only IIT but scoop sampling plus small punch test and the IIT, and we compared the results of what we obtained by small punch test and IIT. It was incredible, because the difference between results what we obtained by IIT and the small punch test was about 1 or 2%. So we said, it's very, very nice. It was very nice. It was very good experience for us. We did more, of course, these turbine rotors. And all the time, the differences between small punch test and IIT wasn't higher than 5%. Only shortly, I would like to say the conclusion of the work what we did with our teams. We can say that we try to develop the system what is fully non-destructive, cost-effective method, what is cost-effective for preventive material analysis. It should be portability, to be possible to use it almost everywhere, mainly in industrial conditions, in different locations. And I would say we were successful. but of course now it is the system is used at this moment is used only in power plants in nuclear power plants. And my personal, we can say, remark that Johann August Brinell, as an inventor, would surely find satisfaction in knowing what is to unfold as a result of his pioneering efforts. Thank you very much for your attention. And I would be glad for your, of course, your questions. If it is possible, I will answer, of course. And my last remark, you can see that we created the system, not only machine, the system, and you can see our family, and because the system is something a little different than only one machine, because if I will calibrate one sensor or two sensor, you have to get the same results. And after we can say some testing, I can say we have system. Thank you very much once again for attention.
Thank you, Daniel, for this excellent lecture. And I'm sure there are questions from the audience. You can type in your questions in the chat box. And if any one of you would like to kind of speak, then you let me know your preference, then I will enable the mic for you if it is possible to speak. Okay, so here is one in the chat box from Chandan Kumar. How are you measuring the indentation depth? Is it the measurement of indenter's movement or something else?
Yes, measurement of the depths, it's the most important thing. How we measure it, we find a way how to measure it to avoid the compliance of the machine. As I said, yes, so we measure it by the sensor. Honestly, I wanted to say that the measurement of the depths is very, very important. And we have to find the way how to measure it to avoid the compliance of the indentor and the force sensor and so on.
Okay, so what is the issue with testing soft material like pure aluminum compared to steel?
Aluminum alloys we measured too. I mentioned that we have only four models at this moment. Aluminum is possible to measure. It's not problem. The curves are very nice. We did not only measurement of the aluminum what was casted, but of course aluminum what was printed, 3D printed too. The result, we don't have a, we can say, finished model, but at this moment I can say that the model will be finished, and the behavior of aluminum is very similar to behavior of the steel. So I don't expect that we will have big problems with evaluation.
I think, it again depends on the pileup and the sink-in response during the plastic deformation. So you may have to use some correction factors. I think Chandan Kumar, you might want to look at some of my publications where we talked in terms of what is the way to correct the depth of penetration or the diameter of the penetration for different materials. Okay. So
To tell you honestly, I told you that we have 4 models, and every model is created by different way of calculation. Yeah, so at this moment I don't know if we can use some of the calculation from, for example, what is similar to austenitic steels, or we have to find another way how to calculate it. Yeah, so really I don't know at this moment, because we don't have experience. I told you that we are creating the model for copper because we obtain some material from fuse reactor from and some guys have got they are very interested in testing copper, what is for cooling in fuse reactor.
the next question from Murli Mohan. How do the data compare with other methods?
Okay, could you tell me more? How do you mean it? How do you mean it?
What is the comparison between the instrumented indentation test result versus what you get through maybe a standard test method?
In the presentation was shown that the comparison between standard tensile test and IIT test after the evaluation is up to 10%. For P91, P92 is less than 4-5%. At some materials, we can speak up to 10%, and for fracture toughness, up to 20%.
So there is one question from Kumar Abanindra. He's asked about, can IIT be used in overhead conditions, meaning maybe inverted conditions?
What conditions do you mean? What kind of conditions do you mean?
I don't have his elaboration, but overhead conditions, can you just type in what is that you mean by overhead conditions? And in the meantime, I think there is a raised hand. It's upside down. That is what he's saying. So supposing you have a pipe at the top and you want to do that.
Yes, the results are completely the same when you use this machine in vertical or horizontal or upside down position. We tested it, and I can say that it doesn't have a problem to use it in any position. Because, for example, pipelines in industrial conditions sometimes are available only from downside. Yeah, so yeah, it is necessary, and it is possible.
And there is one more follow-up. Can the indentation test the mechanical properties of reinforcement material like glass, carbon fiber, and resin-based materials? I think you are working on that, right?
I mentioned that the material should be softer than is indentor. Indentor is made of the tungsten carbide. So testing the glass, really, I don't know.
No, he's talking in terms of polymer composites, glass fiber reinforced composites.
Yes. Now, yes, polymer is very good question. One doctoral thesis of our student is done by testing of polymer. Precisely, I am speaking about the Grillon and Grivori. These materials are injected into the forms and are used for production of wheels in automotive. And now we are creating the model for evaluation. But the polymers behavior, I'm speaking about elastoplastic behavior, is completely different, and it's not easy to develop this type of the model for evaluation. But at this moment, we have one. We can say I am not fully satisfied with this model, but our team developed one, we can say, preliminary model for this.
There is a raised hand from Dr. Kundan Kumar. Maybe he can go and speak before I take the next question.
Daniel, very nice presentation.
Thank you.
Actually, my question is whether only single model will be workable for all type of materials.
If the single model can be okay, no, one single model can be for only one group of the materials. Yeah, materials would have the same behavior. Yeah, and so if there is a group of material with the same behavior, of course it will be enough for one model. But I don't think so. I think that everything is about the behavior from the point of view of the hardening, and if the principle of the hardening or the curve of hardening is completely different, so you have to use for description a completely different model. Yeah, so as I said, only for what we can say group of material can be this when can we have one model.
Okay, then I think your machine works on the Mayer's principle, some correlation-based technique it is there. So, are you calculating?
Hello.
I'm sorry, we were interrupted a little, so I didn't hear the full question.
Yeah. So I think the machine is working on the Mayer's constant and hardening exponent, something like that. So do you have a correlation for anisotropic material also, means different property in different direction?
At this moment, we have only 4 models, as I said. Yeah. The next student work is for biomechanic. Maybe it will be interesting for you, but we don't have a model for this because we have limited time of our mathematicians. So we made a very nice work of indentation of the cements what are used in biomechanical. If you would like to, if you need to have a replacing of the joint, for example, so the cement what is used for fixing the joint was tested, and it was the subject of this testing was that the cement was with some type of antibiotics, and we measured how the mechanical properties are changing based on the different antibiotics what were inside the cement.
Actually, my question is different. I was talking about zirconium material that is anisotropic, which is having not mechanical properties constant.
Okay, when you are speaking about anisotropy materials, of course, you will see it. You will see it on the curves. In the presentation, I mentioned that if it is a new material, the standard deviation of the tests of each curve, we can say, can be 0.2%. But if it is anisotropic material, the standard deviation will be much higher. Yeah? So immediately you can see what type of materials of the material it is, if it is anisotropic or isotropic. Yeah, so you will see it immediately by this type of the test. And you are right, for this type of the material, it is not perfect convenient. Maybe could be interesting to change diameter of the indentor, for example, because all bigger indentor for anisotropic materials maybe can be better. But no, I have no experience in this field. Honestly, I have to say.
Okay,
Last
there is
question,
one
just
more
last
question.
question.
Okay.
You just mentioned about the standard N675, something like that. Are you following any such standard for your machine?
We followed every standard what is in the world. Jingxin Li and his team studied all documents, all papers what were written about automated ball indentation method. So we started with the papers from Hagag, we started from Frontix, we compared our results with Frontix because we had this possibility. Based on these papers, all papers, what is possible to get in the world, we created our work. And of course, I would like to mention one thing. It is very interesting, maybe for you. I said that we started our research in the field of the IIT in 2012, and it is curious that it was based on the return of Karel Matocha, our professor, when he returned from India. And he returned from India, and he said, "Please look at this. Look at this presentation. It's about IIT. I would like to have this machine." So we started to build this machine based on the information from India.
Just take the next question, which is from Mr. Kunal. What is the minimum space required for installation of this instrument and its table in terms of length, width, and height?
Minimum space. We can say the height of the machine is about 300 millimeters. The width is 10 times 10. If you would like to clamp it by magnetic system, so we will need about 40 centimeters in length and 20 centimeters in width. As the height, as I said, about 400 millimeters. Yeah, so that's all. That's all of what you need. Yeah, that's all. What is convenient for you? It is that, or for this method, it is that anytime you have in your everything in suitcases, and if you hesitate, if you measure correctly or not, you will get the reference specimens, and in the suitcase you have a small table, so you can install anywhere, and you can check it if it is the same results or not. Yeah, so this is not only, yes, but you ask me about the space. Yeah, so you need 40 centimeters times 20 centimeters for magnetic clamping.
Okay, so are there any more questions from the attendees? So if there are no more questions, we will thank Daniel for giving this nice lecture, and congratulate him for having delivered this lecture to the Indian Structural Integrity Society as part of our webinar series that we have been doing for the last 2 years. And once again, we will all thank him and congratulate him for his excellent presentation.
Thank you very much for the possibility to have a lecture. among you. And if you have any question, please don't hesitate, and you can write to me the email. It will be a pleasure for me to answer you or to send you more details. Yeah, so anytime. Thank you very much.
I think
Just one
Daniel
request.
used. Yeah.
When this presentation is shared, I can share with my colleagues over here.
Dr. Kundan, I have kind of recorded this. We will post it in the InSIS website. So that time you can probably take the entire lecture, including this, the discussions that we have had. Okay. Yeah. So Daniel, I know you keep traveling. So when are you planning to visit India next time?
At this moment, I don't have a date, but of course, definitely I will come back. Yeah, because I was in India twice at this moment. I know that we have some negotiations with Set3 about delivery the next machine. So I will be in India. Yeah, India is very special, and I will return very glad. Yeah.
Yeah, I will suggest that you plan for a visit during the month of October when we have the Structural Integrity Conference at VNIT Nagpur. So I'm sure you know the colleagues in the Vishwesvaraya National Institute of Technology in Nagpur. So you can plan for the visit during that time. Okay.
Okay, October. Yeah. If you send me some materials, I will consider.
Sure. Okay. So thank you all for having attended this webinar. And with this, I will kind of conclude this webinar. Thank you very much.
Thank you too. Have a good evening. Bye-bye.
Bye.
You were prepared then.